Again, truly an honor to stand in front of you and be able to tell you a quick story of what MIT Nano has accomplished in the last 5 years. You know, October 4, 2018, just 5 years ago, we held the ceremony to honor the fact that we have indeed completed the building, and we held the tours of the building that day. And the scariest thing about the tours is that all the windows of MIT Nano are wide open. You can peer inside, and there is nothing inside because there were no tools inside the facility. We had a beautiful building ready for whatever comes next. What came next is we waited till August 2019 to welcome just about the first users. And from then on, we spiraled into getting more and more and more to utilize MIT Nano. Numbers are vast at this point, over 1,000 individuals. And I'll mention the exact numbers in a bit. But as things stand right now, there was a pandemic in between we had to kind of worry about. There were a few other things we needed to do, like move hundreds of new tools inside. Each one of those led us to the next set of opportunities. And at the end, the question is really where are we heading and what is the next big thing we can develop? And the answer is that we need to put in a perspective of what is our main purpose. And it is to indeed change the world, make a world a better place to live in. So to us, the question was always about, well, the future will be measured in nanometers. And there is this vast opportunity at nanoscale to transform the world in extremely positive ways. But what do we need to do to truly make it that? I had the privilege, right as I was in the midst of designing MIT Nano and thinking about how to build a space for everyone to innovate, to also spend time asking questions of how does the innovation process work? What is it that we do to enable us to build the next set of great ideas? And I'll give you, and some of you might have seen this before, but I'll give you a very quick set of examples of how long does it take to take a brand new idea and make it into something that everyone can use. Give it to 1 million people. I start with a simple example from the beginning of the 20th century, a zipper, a technology that is by far better than a button, but not necessarily easy to make at the beginning of the 20th century because there are no tools allowing you to put small mechanical parts that zipper is made of precisely next to other small mechanical parts to generate active technology known as a zipper that eventually ended up on 1 million boots and making the zipping up of the boots easier than lacing. Indeed, the journey took about 12 years from the patent that mattered in 1913 to the one that indeed allowed the growth of, by 1925, of 1 million boots with zippers. You can say, well, that's an old technology, so let's take another one. Velcro, middle of the 20th century. Technology that's brilliant again. Thank goodness there was an Apollo mission using Velcro. That's a good way to advertise your technology. But as things stand, still, it took 13 years to commercialize it because no one knew how to extract small plastic fibers. Plastic was a new idea in the middle of the 20th century, and the idea of manufacturing it, scaling it, simply did not exist. Now, again, all of these sound like older examples, so let's look at the end of the 20th century. A technology known as strained silicon, amazing technology, speeds up all the holes. Electrons and holes are carriers inside your wafers that pass the current and consequently make your transistors work faster or slower. If they can move faster, those holes, they would give you faster electronics. And the way to do it is strain your silicon, separate so-called heavy hole from the light hole. Brilliant, simple idea. All you need to do is take this wafer and replace it with one that has a little bit of strain in it, and everything else stays the same. Still, it took 13 years for this technology to be commercialized, only pushed by the desperation of industry of saying, can we go ahead and make a more competitive transistor because we are reaching the end of the conventional way of making technologies. Let me give you one more example, because you can say, well, this is 20th century, and how about 21st century? Well, another technology known as high-K dielectrics, higher index of refraction materials or high dielectric constant materials that can be inserted inside the silicon flow, hafnium oxide rather than silicon dioxide, itself can provide you lower voltage operating transistors. Voltage squared gives you the scale of the energy you're going to be spending. Lowering the voltage by a factor of 2 reduces the energy by a factor of 4. Fantastic idea. It still takes over a decade for this idea to actually be commercialized. Whenever you invent something new in the lab, my message to you is Don't expect that the following day people will accept it and grow it into a technology that millions of us can use. It takes a decade plus to actually take the basic nascent ideas and develop in the academic laboratories and give it to the world so the world can be a better place. We actually often think of it as if there is a foundry, and a foundry can be the machine shop to make zippers or an extrusion plant to extrude the Velcro, or indeed the foundry of silicon electronics. If there is a foundry, you can accelerate your journey. But many of the brandest, newest ideas, the ones on nanoscale, are using new materials in ways that have never been used before, necessitating a need to develop an entirely new branch of scaling it up, proving it, accepting it for whatever purpose is out there. Here's a longer journey that took a while to do, about 30 plus years. And it's a journey of so-called colloidal quantum dot technologies. Invented in the 1980s, by 2010s, 15s, 13s, you start seeing the first technology using colloidal quantum dots. Colloidal quantum dots are little chunks of stone. Depending on the size of the stone and chemistry of the stone, it can glow any color of the rainbow. First times around, it didn't glow very well, but then scientists, chemists figured out how to make them work extremely well. My colleague Mujiba Wendy being one of them, who figured out how to actually make the quantum dot extremely efficient in its luminescence, which by itself meant here's a beautiful lumophore, something that could be used in large-scale opportunities. Well, where would you use it first? Well, of course, I would love to make a display technology out of it, but that's too hard. Displays have 1 million pixels, 4 million pixels. I need to make different color pixels. Oh my gosh, huge amount of work needs to be done to make something like a display work. But a simple thing to do is to use a colloidal quantum dot and say, I would like to make a light bulb that looks as good as an incandescent light bulb. And because although LED light bulbs are more efficient, if I have a bowl of fruit and I illuminate bananas with them, bananas don't look that good under LED lights, unless you can take an LED light, color it with a little bit of quantum dots by taking some of the blue, down converting it to red from the glow of the red quantum dot, and combined you can generate illumination that mimics that of an incandescent light bulb, except at about 4 to 5 times more energy efficiency compared to incandescent light. So that sounds like a fantastic idea. All you need to do is figure out how to scale manufacture of colloidal quantum dots and how to make them maintain their efficiency when you spray them or slot die coat them over large areas to generate films that will be luminescent films. That will be the ones that will provide you the glow that you're looking for. A startup company from MIT, started by graduate students, working with myself, working with Professor Wendy, realized that we might be able to actually do this. They're called Q Division. Q Division started making really nice light bulbs. And in 2009, 2010, it made sense. If I'm 5% of the value of a $40 light bulb, and that's how much LED light bulbs cost back then, that's a $2 per light bulb. But as the price of the light bulb started going down to $1, 5% of that is not very much of a business. I need a more expensive light bulb. So the solution was very simple. Look at where do you find LEDs that need to be glowing and are more expensive. And TVs happen to be those chunks of technology we use that happen to have $20 light bulbs inside. Go ahead and replace their glow with colloidal quantum dot glow, and you can make a TV like never before. Now known as a QLED television set. Why? Because in 2016, Q Division was acquired by Samsung, and today's their technology, colloidal quantum dots, used in television sets is about $4 billion market, enabled through the fundamental understanding of how to make a quantum dot, enabled through the fundamental understanding of how to improve the efficiency of the quantum dot, how to coat it, how to combine it with the existing technology, utilizing the foundries of making TVs and then modifying them through the introduction of the quantum dots. Journey that is not trivial by any means. And indeed, when we first demonstrated this in 2013, 10 years ago, we did see that there are additional things that could be happening with this technology. But even 2013 was already 30 years from the very first instantiation of demonstration of first glow of the quantum dots. Took many steps and many people to make it just right. And hence the nanoscale opportunity is vast. And yes, it does get recognized once in a while. For example, October 4th, exact 5th year anniversary of MIT Nano, our colleague Munji Bawendi was recognized with a Nobel Prize in Chemistry for being the one to generate high-efficiency colloidal quantum dots, together with Louis Bruce, Alexei Ekimov, who indeed identified the presence of colloidal quantum dots as something that could be valuable for the world, but not perfected in the way Munji has done it. Of course, I had to take a photo with him that day. We are close colleagues. His work on colloidal quantum dots, though, is one of the many examples of what's coming. And his most latest work on a different kind of quantum dot is imaged here at MIT Nano, is an image of a perovskite quantum dot. This is a quantum dot that shows the first direct evidence of interference between indistinguishable single photons sequentially emitted from this perovskite nanocrystal. What does that mean? Well, you have found a source of repeatable light, always the same, always perfect, with high efficiency, and consequently could provide us new ways of generating quantum cryptography, quantum computation. Sources of indistinguishable photons have been a holy grail for many, many of us. This is not a technology yet, but it's an inkling of controlling the nanoscale in ways that has not been done before to generate that fundamental element that we have been missing. And indeed, there's a lot more work to be done, but it gives us the first step, enabled through the tools of nanoscale. Once you make it, you might want to position this quantum dot exactly where you want it to generate a single photon emitter, at which point you might turn to the work of Professor Farnaz Nehroui, who uses her colloidal quantum dots, in this case metallic ones, but they could be used for perovskites as well. She has a separate technique for it, to assemble these nanocubes exactly where she wants them, with precision that has been previously unprecedented, at high yields, giving her exact control of nanoscale over a very large area in repeatable fashion. One thing you can do with such technology is actually make an entirely new way of making a switch, an electrical switch that doesn't use any semiconductors. You can put a metal, another metal, separate them by some organic molecules, that molecular spacer in the middle of the slide. If you provide a little bit of mechanical force, you'll compress the two. How do you apply mechanical force? Apply a little bit of voltage. The two, top and bottom, will be brought together. And as a result, the current, so-called tunneling current from top to the bottom, will increase. How much? Well, in this case, 100,000 times. You just made an electrical switch that has no semiconductors. It has a chunk of metal, another chunk of metal, atomically flat, separated by nanoscale thick film of molecules that are squishable. So let's call this particular device the squeezable switch, or the squitch. It could rethink the way we think of electronics. Will this replace tomorrow's Intel chips? Certainly not. But will it, in 10 years, be a relevant technology to consider in thinking of a different way of making electronics? Very likely. At least it would inspire another branch of rethinking of what electronics should look like. There are many more examples of using nanoscale in ways one could not have accepted before, or at least could not have predicted, given that we didn't have quite as deep of a view of how nanoscale truly looks. Here's a work of Ronan Han and Harry Lee that uses molecules, in this case rotational transition of carbonyl sulfide, that due to the rotation, you can monitor that rotation and use it as a clock. How accurate of a clock? Almost as good as an atomic clock. The nice thing about it is that it doesn't require contraption that is this big, that cools down your particular chip and gives you the specificity of making an atomic measurement. That's almost as good as an atomic clock and could be compressed down to maybe a cubic centimeter in a total volume. A game changer. If every chip had an atomic clock, we would have perfectly precisely synchronized electronics around the world. That can change the way we think about what the electronics of tomorrow looks, enabled through the control of nanoscale and integrating with conventional electronics as we know it. And this is just some of the many, many projects one can imagine. These are examples of the types of chips our community makes. Many of them touch MIT Nano in some way or sometimes completely. We don't make every single element of these chips, and we don't need to. I mean, there are foundries, but we should add the value add element of it as you're enabling to use of the tools of MIT Nano. Advances in electronics are vast, coming our way. Is it three-dimensional integration of CMOS for rethinking how to put together existing materials, ultra-wide bandgap materials for high-power electronics, nanoelectronics for AI, 2D materials and devices, chiplets where you put various chips on top of each other. Professor Jesus Del Alamo later today will lead a session describing all those opportunities and more through the electronics. So rather than anything more, my job here is to be a teaser for many of the ideas you're about to hear from them in the sessions that follow. Quantum computing clearly is another thing to consider. Professor Will Oliver with colleagues will have a chance to tell you a story in the session that follows this one, how to generate the next quantum computing age. What is it that's needed? What are the big challenges? This is just one of the many publications that his research group and others around MIT have done. This one is in using 2D materials, ultra-thin materials to reduce the size of superconducting qubits that may pave the way for personalized sized quantum devices. And indeed, there are many things that one can develop within it. Is it superconducting qubits, or is it coherence and gate fidelity? Integrating these in 2D arrays that are indeed coherent across the array and consequently can generate the quantum computations you're hoping for. These are materials challenges, nanoscale challenges that all of us need to figure out how to make working. And in order for us to do so, we need to be able to peer down at the nanoscale and rediscover these fundamental principles that can then lead to these entirely new sets of technologies. One of my favorite things to think about when it comes to new materials is asking them, can you use them as semiconductors that provide you an entirely new pathway to maybe making electronics? In this case, making solar electronics. This is a picture of a solar cell made on a piece of fabric at MIT.nano using molecules, carbon-based materials, that are dark and absorb the light and generate electricity in return. It's a solar cell that has 100 times less weight than conventional photovoltaic. It's not as efficient as conventional photovoltaic, but per kilo, per pound of this cell, you will get 30 times more power. Deploying these cells across the world becomes a lot easier. And the processing methodology for making them is as simple as slot die coating. This, by the way, is slot die coating of perovskite thin films. Those can generate 20% efficient solar cells, matching silicon, even exceeding it, in the labs of MIT.nano, and looking at ways of scaling them up for large area production purposes. Once you make your solar cells, you need to store the energy of them. Well, where do you put it? How about in the foundation of your home? How about using the concrete of your home that builds your foundation as a supercapacitor? Sounds crazy, but we already use the material, concrete, so we might as well make it functional. That goes beyond the function of holding your house. Add to it a few additives. Ask Professor Franz Josef Ulm, Admir Masic, and Yang Shao Horn how to do it, and I'll show you some pathways. That image on the right is an LED being powered by concrete supercapacitors. It does change the way we think about what the future of your homes might look like. Indeed, your solar cells up on your roof will collect the energy during the day, your foundation will store it, and then at night you use it when you need it. Rethinking the materials themselves also allows us to design them down mechanically on the nanoscale. So work of Carlos Portello at MIT.nano allows him to make the material that is stronger than Kevlar and lighter than Kevlar so it's stronger for the same amount of mass compared to Kevlar, and consequently gives the ability to generate extremely strong materials. Why does it happen that way? Because it happens to be nano-designed or micro-designed, in this case using our 3D technology, printing technology, that should be scalable one day, and giving us an entirely new way of thinking how to make the strength in the material thanks to the appreciation of the nanoscale properties of it. I love work of many of my colleagues. I particularly get tickled when I see the work of Kripa Varanasi that's both transformational as well as entertaining to show. So he spends time asking how to use nanoscale coating to change wettability of surfaces, for example. Of course, one reason for doing that is right as MIT.nano was opening, he was demonstrating these types of technologies that allow you to get the last ounce of ketchup out of your ketchup bottle. Tremendously valuable technology that has since the opening of MIT.nano been translated to other purposes. Indeed, if you have a toothpaste that is dying to come out of your toothpaste bottle, you can do a lot better with that elixir technology on the right than you would suffering with the usual toothpaste on the left. Now, that is controlling wettability for the sake of making the surface more slippery. What if we did it the other way around? And indeed, conventional spraying of a liquid onto a surface might lead to something like this. However, if you engineer the liquid itself, you might be able to generate a stiction that otherwise is unachievable. Why would this matter? It matters for pesticides. We use 50 times more pesticides than we need. 49 of those parts of pesticides go into the ground and are responsible, it's estimated, for 200,000 deaths a year thanks to the pesticide pollution. If we can reduce the amount of pesticides by making the liquid of the pesticides more sticky, by the way the leaves of the plants are designed to let the water slide off of it, well, if you go ahead and use these new liquids that Kripa Varanasi's group and a little startup called AG-Zen came up with, you will avoid a beading, and consequently you will generate coating using a lot less poisonous materials. Again, another technology that demonstrated 10 times reduction in spray volume in the lab using this. Coatings can be used anywhere. Again, nanoscale coatings in the form of silk that Professor Benedetto's work has looked into is there to make your bananas last longer. If you wrap the banana into protein with a silk protein, you'll be able to maintain its longevity. If you go ahead and happen to have veggie noodles and without, and to the left and on the right, with coating of this edible protein, you will be able to make your foods last longer. 10% of the produce in the warehouses gets wasted before it ever gets sold. Can we save it? Can we save the food in ways we couldn't before? Can we save the seeds that happen to be used to grow those plants? And the answer is yes. This technology is pioneered by a startup company from his group called Mori Technologies. Indeed, many other things one can expect you would be able to build. This here is an example of using the very same silk as an alternative to microplastics, making them biodegradable microplastics for cosmetics, coating, and such other purposes. Coatings themselves can also provide entirely new material sets that, if you look down on nanoscale, you realize they can behave in ways you did not expect before. This is a so-called ferroelectric domains on a material that's van der Waals bonded, a van der Waals solid, so 2D tin selenide. On the left is an image of one of these flakes that's been deposited. On the middle and the right is that very same image, except now imaged for the ferroelectricity. And you can start seeing those dark and white lines that are ferroelectric domains. Every line is a separate ferroelectric domain. What nanoscale allows us to do is rethink memory technology, rethink switching technologies that could be utilizing this kind of material set. Observing the nanoscale gives us ways of rethinking who we are and what we can do. So the previous observations of the carbon nanotubes, I've shown you very small objects. What I've shown you a moment ago in this image is an example of a 3D printed object that we have then gone ahead and imaged, being able to peer into the nanoscale itself. Or the work of Deblina Sarkar, a professor in the media lab, looking at ways of positioning nanoscale antennas in exactly precise locations. These antennas are so small they can sneak between the cells or actually get into the cell and transmit from within the cell what is happening inside it. Is the pH balance or ion flows and so forth. Insights that will give us ways of rethinking medicine as well. I love this image, which is the Andy Warhol-inspired rendition of MET18. MET18 is a scaffold protein for iron-sulfur protein maturation inside the cells. Work of Professor Kathy Drennan that has indeed just one of the many examples of the crowd transmission electron microscope at MIT.nano providing insights into the new ways of seeing biology. Professor Thomas Schwartz will lead a session later today showing you many more ideas that have indeed emerged through MIT.nano ability to be able to image these nanoscale proteins over the last few years. I'll conclude by showing you just a couple of more slides. Professor Jim LeBeau has pioneered ways of seeing the nanoscale like never before. This is an image that shows you features down to a fraction of a nanometer, 0.1 nanometers, using conventional imaging technique of electron microscopy. Notice that image on the upper right. It looks like a blurry image of aluminum and nitrogen, aluminum nitride. Is it really there? Well, take a look on the right, on the upper right of the right image. That indeed is. You can see individual atoms of aluminum and nitrogen using technology, a technique that his group pioneered, improved, and indeed made significantly better, to be able to see down at a level of 28 picometers. Through introducing computation into the imaging itself, you can generate a tremendous amount of more insight into how the world is put together. The resolution that he shows there of 28 picometers is essentially limited by the thermal vibration of the object. That is why it's so big. If it's cooler and vibrating less, you should be able to see even lower. But it requires entirely new insights using the tools of Nano and the brilliance of the researchers who use them. We have 160 tools at this point at MIT.nano. We have 1,156 users in the fiscal year 23 that closed in July. That's many people given the fact we had 0 users in August 2019. And indeed, our growth is exponential when it comes to bringing in externals coming in. Fantastic staff of MIT.nano maintain operation of such facility as we have it. Every department pretty much at MIT is represented, 50 DLCs. We have about 344 leaders, PIs, about 250 from MIT and about 90 externals. Is it leaders of companies? Is it new PIs or professors from other universities that utilize us? We're doing fine, and we are extremely excited about what's next. At this point, only 2/3 of MIT.nano footprint is occupied by tool sets, and that's exactly the way we wanted it, knowing that we need a decade or so to grow. In 5 years from now, the building will be completely filled. And at that point, we'll be probably at about 2,000, if not more, users. And hopefully, I'll be able to tell you the next set of Nobel Prize-winning discoveries that were initiated 5 years ago. It is indeed tremendous opportunity that's ahead of us. Thanks to the fact that the facility is not just the tools, but because we have an incredible staff team that is maintaining and being the domain experts to lead us forward. We do think support of the startups is extremely important for our ability to do what we really need to do for the world, which is provide you with the next set of solutions. The startups are the key next step to many of our students. 1/4 to 1/3 of MIT graduates will initiate a startup or join a startup upon graduation. Being in a startup ecosystem is not an accident anymore. It's not something that you will maybe do after you finish MIT. 1/3 of the students upwards will actually go ahead and do it. And as an educator, I think it's my responsibility to ensure that you know your physics, you know your mechanical engineering, and you're really good in programming, and you also understand what entrepreneurship means on an equal footing. I need to give you the tools to build that next set of grand ideas. We started a program 2 years ago. We are now starting a 3rd year of it called Start.nano, where we offer every startup a discounted use of MIT.nano facilities. And by every startup, I mean a startup that happens to match well what we can offer and what they need. 34 startups are presently in the program. We have overall about 130 companies that use MIT.nano, maybe 50 startups overall. You know, the ones that are perfectly matched to us, we see about 34 of them. We give them discounted use of the tools as well as training programs so that the future big company CEO, CTO understands what does it take to build that next idea. We often think of MIT.nano as being perfectly designed for this innovation cycle. Innovation, by the way, is a journey. Invention is patent that happens like this. Innovation is the 10-year journey that follows. And a 10-year journey for hard tech is not fundable experience. If whatever I need to do over the 10 years to make a new hard tech technology succeed, well, it's going to require me about $100 million of operating expenses, development expenses, tool building, to go ahead and build that brand new idea. Result of it is that many, many, many technologies never become matured, simply because they are too expensive and take too long of a time. If I told a VC today, listen, in year 2033, I'll make what I want to do right now into a technology that will be beneficial. All I need, dear friend, is to give me $100 million, and in 2033, I promise I'll give it back to you. Oh, wait, you want something more than 100 million? You want it 10 times more than that? Well, sure. All right, so I'll promise you this. I'll give you $1 billion 10 years from now if you give me 100 million right now. It's a good deal, right? Trust me. Anyone rational should not trust you, because they can make the same kind of return on investment if they think they know how to play the stock market by investing in essentially variety of derivatives and whatever else they know how to invest in over 10 years. A tenfold increase is what the good VCs expect. So as a result, venture capital community that spends $150, $160 billion annually doesn't invest in hard tech. 1 to 3% of the VC money goes to hard tech ideas that we are developing, which means we'll never grow the next technical idea unless we can use MIT Nano in some way to make that idea a little bit quicker to be developed, or at least make it appear that it can be developed a little bit quicker and for a little bit less money. I've admired many of my colleagues that I've learned from. Professor Fiona Murray taught me a lot about innovation. My students, Dr. Rich Swartworth, drew this particular graph after many times we talked to each other about innovation. And recognizing that the value of death really comes in 3 forms. There's a value of death of an idea, and that simply means that I have an amazing idea, but no one believes me. And I need a little bit of money, $500,000, few $100K from an angel investor to get going. Only about 1 in 10 ideas, the best we can estimate, indeed succeeds and moves to the next step of being able to build a prototype. Well, of the ones that are going to raise enough money to build a proper prototype, only maybe a quarter will survive. And again, you lose a lot of tremendous opportunity. And once you do have a prototype and you present it to the world and say, all I need is the remaining $85 million to build a factory to actually 5 years from now give you what the world needs. Well, maybe a third of those also survive. Overall, if you multiply those numbers, you'll find that less than 1 in 100 companies will indeed become. And out of the ones that actually get the final stage, only 20% of them will actually give you something that will truly, truly make you money. But one thing we can do is recognize that the first part of the journey, those first 2 valleys of death, that takes about 5 years. And those first 2 valleys of death are relatively inexpensive. That's maybe a $15 million journey. Still a lot of money. So can I make it less? Well, the goal is with star.nano to indeed do that. Can I make that valley a little bit shallower? Not quite as deep. I won't give you all the money you need because you need to prove yourself. But maybe I can, for 15 million, maybe it's 3 that you need over the course of 5 years. Because if I can get you to the end of year 5 with a prototype in hand, you can now stand in front of a VC and say, in 5 years, I'll triple your money. That's investable. Our goal is not to choose the winners. Our goal is to make sure that there are more hits on the goal. Indeed, I can't tell you which technology will succeed because there are many things that need to go right. Technology is only a quarter of the success. The other 3 quarters have to do all about stakeholders and the ecosystem and the way you put together a team, the scalability and the supply chains and so forth. Things I can't control, hence why not everything succeeds. But I would like to make more things succeed by giving you more things to choose from, more things that can be brought to 5 years for cheaper, consequently, more ideas. That's what MIT Nano should be able to do. And through that, use the 100,000 square feet of our laboratory space that's available for any grand idea to build that better world. Thank you so much for your time. I believe the next thing we're going to do, I can answer a few questions. So will MIT have a role in the Microelectronics Commons? The answer is absolutely yes. Microelectronics Commons has recently been announced. MIT played a pivotal role in securing the Northeast Microelectronics Coalition hub. We are working really hard to ensure that the region gets lifted up through our own work and a partnership with many of you, actually, who are in the audience. MIT Nano will serve as a core facility together with MIT Lincoln Lab so that anyone who would like to build their ideas across the nation can come to MIT and indeed build that next set of grand ideas. So yes. What excites you most about the CHIPS Act? I think what is remarkable about the CHIPS Act is what we have seen as teaming over the last few years. What is incredible to me is the amount of conversations we've had with our partner entities. Is it companies? Is it startups? Is it government agencies? Talking about microelectronics. In the last 2.5 years, we have talked more to each other than we have done in the last decade. And through that interaction, we have generated perfect appreciation of ideas we could not have done on our own. So I think the CHIPS Act, although only just started funding new opportunities like the Microelectronics Commons, has already succeeded in bringing us together and generating an ecosystem of discourse that did not exist before. What would you consider MIT Nano's biggest success in the last 5 years? I've shown you a few, and mind you, there are 1,000 users. I probably understand maybe a couple of hundred of what the projects they are doing. Of those 1,000 projects going on, I'd say 10% are extremely, extremely good. But I don't have time to show them all to you, so I skipped a whole bunch of them. Look around. There are annual research reports online. Engage people when you walk through MIT Nano. The most dangerous question you can have on MIT campus is asking them, what are you working on? And the next hour of your time will be spent in mesmerized talk to your colleagues. So thank you very much for your attention. I would like to move us on to the next stage. I would like to ask my colleagues, Will Oliver and his colleagues, to come over and tell us more about quantum engineering. Thank you very much. Thank you.